What happens when the largest rocket ever built by humanity faces a catastrophic failure mid-flight and still manages to accomplish the majority of its objectives? On Starship's Flight 12, the booster was lost before touching the water. An engine failed during the ship's ascent, and yet the mission may have been one of the greatest technical breakthroughs SpaceX has ever recorded. How is that possible? The answer reveals a great deal about how space engineering actually works, and about what SpaceX is building for the future. On the eve of the launch, the atmosphere was already tense. A scrub had frustrated everyone the day before, and when the countdown resumed, there was a mixture of excitement and skepticism in the air. But this time, something was different from the very start. No prolonged delays, no launch window being pushed forward. At 5:30 p.m. Central Time, exactly as planned, fueling operations began. The updated systems at Pad 2 once again demonstrated their efficiency. Enormous quantities of cryogenic methane and liquid oxygen were loaded into the vehicle at an impressive rate. Engine chill-down procedures also proceeded without issue. This matters more than it might seem. The ability to fuel rapidly is essential for any high-frequency launch operation that Starship intends to support in the future. There was also a detail that added even greater symbolic weight to the mission. NASA Administrator Jared Isaacman was present at Starbase to watch the flight. His presence signaled something important. Starship is no longer merely an isolated experimental project. It is becoming a central piece of the United States space exploration plans. Then came the moment that made everyone hold their breath. With less than 40 seconds to launch, a hold command appeared. Immediately, those watching must have relived the scrub from the previous day. But this time, the countdown simply resumed. No restart, no rollback, no cancellation. That in itself was a victory, because it confirmed that SpaceX had corrected the issues in the engine ignition detection system that had caused the previous abort, and had done so in under 24 hours on one of the most complex launch systems ever built. The liftoff itself was cinematic. Water blasted upward from the flame trench, creating a curtain of mist around the vehicle. All 33 Raptor engines ignited, and Starship climbed through the skies above Starbase. No immediate damage to the pad, no failures in the launch structure. The initial ascent was visually smooth, but soon, the booster and the ship went their very different ways. Booster B-19 started well. However, approximately 1 minute and 43 seconds after launch, one of the outer engines shut down unexpectedly. One of the most widely discussed theories involves the removal of part of the thermal shield that protected the Raptor 3 engines. SpaceX apparently decided that the improved reliability of the new engines justified reducing that protection. But the environment around the Super Heavy remains extremely aggressive. Intense vibration, shockwaves, heat, and mechanical pressure that few systems can withstand for long. If an engine suffered damage or instability, that may have triggered problems in adjacent systems. Even so, B-19 reached stage separation. The vehicle's multi-engine architecture provides sufficient redundancy to continue operating even with one unit down. 2 minutes and 23 seconds after launch, the booster shut down most of its engines, keeping 5 active in a symmetrical configuration. What came next was baffling. Between approximately 2 minutes and 32 seconds and 2 minutes and 49 seconds, the booster's engines began firing in a highly irregular pattern. Some ignited, others shut down, others reignited across different rings. The visual configuration barely resembled anything seen on previous flights. The thrust appeared asymmetric, with one side visibly more powerful than the other. This behaviour was likely part of the new active spin procedure developed by SpaceX. In earlier versions, the booster relied on the dynamics of the hot staging separation system to initiate its rotation. With the most recent updates, SpaceX appears to be moving towards a spin controlled directly by the engines, more aggressive, more dynamic, and, as became evident, considerably more complex to execute with precision. B-19 continued descending towards the Gulf. Atmospheric pressure increased, airflow became visible around the engine section, and the ocean appeared on the cameras. Then came the landing sequence, or the attempt at one. Around 6 minutes and 11 seconds after launch, the landing burn was initiated, at least partially. But almost immediately something seemed wrong. At approximately 100 meters above the water, the booster was still traveling at a very high speed, incompatible with any controlled landing. The onboard camera feed cut off abruptly, which strongly suggests that B-19 was destroyed before reaching the water's surface. SpaceX later confirmed the booster failed to ignite all of the planned engines during the return burn, performed the partial burn that ended earlier than expected, and attempted to reignite the engines for the landing burn without success, resulting in a violent impact in the Gulf. Comparing with previous flights, the landing burn was initiated with far less lead time. On earlier missions, ignition occurred more than 15 seconds before water contact. This time, it was a matter of seconds. There was not enough time to decelerate adequately. The aerodynamic stress, combined with the extreme velocity, likely destroyed the vehicle even before impact. The probable causes? Timing issues in the commands during the high-pressure atmospheric descent, or damage caused by the repeated ignition cycles during the active spin, which may have compromised engine availability in the final critical phases. Investigations are still ongoing. But whilst B-19 was facing those problems, Ship S-39 was having an entirely different day. 2 minutes and 27 seconds after launch, it successfully activated all 6 engines. Around 3 minutes later, one RAPTOR vacuum engine appeared to fail. Subsequent footage showed the engine inactive with unusual smoke around it, but the remaining 5 continued operating and the ship met all of its ascent objectives. SpaceX confirmed the completion of the ascent burn and the successful start of the orbital phase. Around 17 minutes after launch, the payload bay door opened without issue. 2 minutes later, the first payload was successfully deployed. Others followed, including experimental observation and communications hardware, some fitted with external cameras designed to film Starship itself in space. The result was one of the most striking moments of the mission. External footage of Starship drifting through space, captured by its own payloads. The engine relight in space also appears to have been successful, another critical milestone for future orbital operations. Re-entry began at around 42 minutes into the flight. Plasma formed around the ship as it endured nearly 20 minutes of extreme atmospheric heating, and S-39 handled it remarkably better than previous versions. The flaps remained operational, the heat shield showed visible improvements, the severe oxidation marks that characterized earlier missions were largely absent. A clear sign of progress towards reusability. The landing burn occurred shortly after 1 hour of flight. SpaceX intentionally activated only 2 engines, simulating a landing scenario with an engine-out failure. The ship descended in a relatively controlled manner into the ocean, remained structurally intact for a few moments before toppling over and exploding on contact with the water. What appeared to be a disaster was, in fact, a planned test, and the crowd at Starbase celebrated. In total, Flight 12 delivered a successful ascent, stage separation, payload deployment, orbital phase, engine relight in space, improved heat shield performance, controlled re-entry, and a landing test simulating an engine-out failure. Even with the loss of the booster, the list of achievements is substantial. And as Starship continues to evolve, NASA is also advancing a technology directly tied to the future of space exploration: orbital refueling. SpaceX's lunar plans depend on the transfer of cryogenic propellant in orbit. and NASA is now developing its own capability in this area. Soon, the agency plans to launch a dedicated mission to study how liquid oxygen behaves in microgravity and to test cryogenic fluid management technologies over several months. The ultimate goal is fuel depots in orbit, space filling stations. The project is especially relevant to the Artemis program, as both Starship and other lunar vehicles depend on cryogenic propellants, and long-term storage in orbit remains one of the greatest open technical challenges. If this mission succeeds, orbital refueling could become a standard component of long-range space travel, an idea that seemed distant just a few years ago, but which is now becoming a concrete reality. Starship's Flight 12 was not perfect, but in space exploration, consistent progress is worth more than occasional perfection. And this flight delivered progress in abundance. If you want to keep following every detail of Starship's development and the future of space exploration, subscribe to the channel and give it a like. Every interaction helps this content reach more people who share this passion for space. Until next time, and keep looking up.